Start now. All right, so checking I'm recording, checking I'm on the right document. All right, so beams. Oh, hi. Yeah, question?
Where are the recordings?
Oh, I'll tell you later. It's on my YouTube channel. Yeah, I got a YouTube channel. But I'll tell you during the break. All right. All right. So, okay, the workshop. So today, we're going to be talking about internal forces in a beam. I'll describe to you what distributed loads are and what they do. And then I'll tell you the methods that we use to graph the internal forces as they vary along a beam. And I've got 4 questions for you. In my workshop, like yesterday evening, I only got through 3 questions because I actually realized each question took a while to explain because there's just so many little things that is required to understand how it works. So we'll see if we can get through all the questions. Otherwise, I'll just give you the gist of how question 4 works. Okay. So, back to the course structure. So we're still talking about statics at the moment. We're not going to jump to dynamics until like week 7. We've kind of covered the basics now, so now at this point you should understand what forces and moments are and what they do. And that will be the focus of your block test on Saturday. But today we're going to talk about a practical application within the realm of structures, and today we'll be specifically focusing on beams. And this will give you some more like context on how forces and moments and how we can use like static equilibrium like in an applied way, I guess, right? So yeah, that's what we'll be covering today. Okay, the first thing I want to talk to you guys about are the internal forces within a beam, okay? And this is basically, I realized last night I explained this too quickly to my other class. There's actually a lot to kind of unpack here, but okay, maybe I'll start with a quick kind of example, right? So if you've got a simply supported beam, like so, and let's say that we've got a uniformly distributed load, as you can see, like so, acting on it, we know that these supports will basically react to those vertical loads, right? So let's just put some example numbers, right? So if this is a UDL, and UDL standing for uniform distributed load, and it applies a 2 kilonewton per meter downwards pressure onto this beam, and let's say the beam is 3 meters long, all right? We're saying that this is going to be a resultant force, or like the net external load that's pushing down is 6 kilonewtons, right? Because you multiply 2 by 3, right? So there's a total of 6 kilonewtons pushing down, okay? And as a result, how the forces want to balance, right? So if we think about Newton's first law and think about the equilibrium of forces vertically, you know that these two reactions want to basically balance out these external loads, these external loads, and as a result, because we've got symmetrical loading here, we actually know that these supports split the load 50-50, okay? So the idea is that these upwards arrows have to balance out the downwards arrow, okay? That's the first thing, right? So that's a simply supported beam with a uniform load applied to it. Now, the idea of internal forces and how we analyze them comes from slicing open this beam, okay? And what I mean by that is like basically when you think about a free body diagram, right? So let me just take a step back. When you think about a free body diagram like we can see here, we're analyzing this like a closed system, okay? Where like we have to have a cutoff point for what we're looking at. So the cutoff point might be, let's just say that's our camera, right? It captures everything that we see here, okay? We're not capturing the sun, the moon, like Jupiter, You know what I'm saying? Like, at some point we have to stop the analysis and limit it to a closed system, okay? So what do I mean by that? If instead we change the camera angle, quote unquote, so that it only captures, let's say, that portion of the beam, okay? Then the idea is that the forces should still be in equilibrium, and therefore the beam should still not be moving, right? So that's essentially what happens when you slice a beam or cut it, okay? So let me redraw this slightly. So I'm drawing half the beam, or roughly half the beam, and I'm showing you like part of the distributed load that we've got, and we've still got that same reaction, etc. And then this is basically 2 kilonewtons downwards per meter. Okay. Except now, right? This free body diagram is not in equilibrium, right? Because there'd be more upwards push than downwards push. Okay. So we need essentially the internal forces within the beam to counteract this, right, and to keep the system in equilibrium. So how that manifests, right, is using our standard directions that we assume for the internal forces, right? And the two I'd like to focus on is shear force and moment, right? So shear force being represented by V, so it's shear force. And M represents, and these are internal, okay? That's your internal shear force, and that's your internal moment, bending moment. Okay, so the idea is that when you slice open the system, it should be able to be balanced, right? And there's another one, right, which I'll show you as well. So N basically represents axial forces, so that's tension and compression. But for a beam, unless the beam is basically experiencing some kind of horizontal external loading as well, so let's say the beam is being pulled for whatever reason, if we've got a pulling force on this beam, I don't know, of like, let's do a different number, of 7 kilonewtons, basically we've got 7 kilonewtons of tension that's induced in the beam as well, which we have to consider. But the vast majority of beams, and all of the beams that we're going to look at in this course, are not going to be experiencing axial forces, right? So beams are generally not in tension and compression, at least like the simplified ones that we're going to be looking at, okay? So I just want to focus your attention on internal shear force and internal bending moment, not the internal axial force specifically, okay? So that's what we're going to map out today. Okay, so back to this diagram. Now this makes a bit more sense, right? The idea is that if you can look at these internal forces from the left-hand side or the right-hand side. So what we just did was we looked at it from the left-hand side, aka we had the camera that captured everything on the left, but you can also have the camera that captures everything on the right as well. And if you do that, you have to point the arrows the opposite way, essentially, because both sides of the internal forces also have to balance each other out in order to get the same signage, if that makes sense. So yeah, essentially, these are our standard directions that we assume, okay? And you'll see, once we do some questions, how we use equations of equilibrium, aka the tools that we've kind of been teaching you over the last 2 weeks in order to solve for your internal shear and moment. That's these two. Let's not really talk about the internal axial force so much today. Okay, any questions so far? Excellent. Okay, so that's the internal forces. Just kind of taking a step back and looking at something slightly different. This is just to provide you more context. Distributed loads, okay? So now we're not really thinking about the internal forces, but I would just like to give you a bit more context on types of external forces that you might see. So what I mentioned briefly a second ago was uniformly distributed loads, right? And here on the left, you can see there's like this concept that there's a resultant force from the cumulative distributed load that you can work out. So if the length of the beam again was like, what did I say before? I think it's 3 meters. And then if this distributed load was 2 kilonewtons per meter, the idea is that if you wanted an equivalent point force, right, you can basically just multiply this by this. And essentially, if you think about it geometrically, you can actually think of a uniformly distributed load as a rectangle, like so, where the height of the rectangle in that dimension, don't think of it necessarily in meters, right? This rectangle is represented by the magnitude, sorry, the height of the rectangle is represented by the magnitude of the distributed load, if that makes sense. So on the y-axis, you're thinking of W, like the distributed load. And then the base of that, or the width of that rectangle, is the length that rectangle acts over. Okay. The other thing to note is the center of shape. Okay. The center of this rectangular shape is in the middle, right? So at L/2 is where the equivalent point force would act, right? So that's kind of how a uniformly distributed load works. Just one more thing I want to point out is sometimes you might see in my notes or other people's notes uniformly distributed loads represented like so. This is a quick way of drawing the downwards arrows, but over time I've actually started using this less because I feel like it's less clear on what it is. So yeah, anyway, that you might see that every now and then in my notes. Okay, so don't be confused. That's just another way of writing the same thing. Okay. Next is triangularly distributed loads, okay? So if we were to think of this, so if I draw an eye, okay, there's an eye looking sideways. If I was standing on the left looking to the right, for the case on the left, what you see is a linearly increasing load, okay? That means this triangle starts at 0 kilonewtons per meter, so on the y-axis, right? Kind of running out of colors. So if I was to draw this like an XY plane, okay? On the y-axis, right, you're at y equals 0, aka W is equal to 0. So let's not consider that as y, that's W. The W is equal to 0, and then it increases. It's got an increasing slope, right, up until you reach W max, which is the peak of where that triangle, of the triangle's magnitude, okay? And then on the right-hand side, this case, again, we're looking from left to right. You have a falling slope, okay? So you've got a linearly decreasing load, and yeah, it basically just goes the other way around. Now, the important thing about these triangles to note is that for a triangle, the center of shape is actually 2/3 of the length of that triangle from the small side, okay? Or 1/3 from the big side, okay? So just keep this in mind because this will come back when we do the questions. So the center of, so if I was to, let's say I've got a piece of cardboard, right, that is like kind of this triangular wedge shape, and I was to like kind of try to balance it on my finger, right? So if this is my finger, like that, that would be the center of gravity of that triangle, right? And so that's the center of shape, essentially, okay? Well, what I'm trying to say is it's 1/3 from that side, or 2/3 from that side, okay? Make sense? Yep, you got a question?
What if the triangle has like different height? Is it always 1/3 and 2/3, or like?
So for a right angle triangle, it's always 1/3 and 2/3. Yeah, so if this is right angle, whether we're looking at it from that side or that side, this would be like h on 3 or like 2 on 3h, or, you know what I'm saying? So if it's a right angle, it's at thirds or 2/3. Yeah. Any other questions for now? Okay. So, next is trapezoidally distributed loads, right? And for a trapezoid, right, just quick like recap. Okay, so let's call that dimension the width. No, that's bad. Let's call that W. Okay, capital W. And then let's call this A and let's call this B. All right. So if we wanted the area, okay, of a trapezoid, what we actually do is we average the two heights, okay? So we get this, and we average it. That's averaged like so. And then we multiply it by the width, okay, W. And that'll give us the area, okay? But what's a little bit harder to find for a trapezoid is the centroid, okay? So the center of that shape, it's a bit more annoying, right? You can do it, but I don't have like a way to do it that's like quick to memorize, in my opinion. So instead of doing it as a trapezoid, when we encounter trapezoidally distributed loads, I would recommend you instead split it up into two shapes. And a trapezoid is really just a rectangle plus a triangle, okay? And so when you're doing the cumulative forces, or the equivalent point load or whatever, you might just want to do this essentially, where you've got a rectangle, and we know from before, a rectangle's centroid is in the middle, and then a triangle centroid is 2/3 from the small side, okay? So yeah, that's one way you can deal with trapezoids, okay? Any questions so far? Yep.
So when you're doing it, do you just treat them as two separate shapes?
Yes. You can treat them as two separate shapes completely and add them together. And the reason it works, you'll see this word come up in many areas of physics, I guess, is the concept of superposition. This is the idea that basically you can get shapes of things, and if the principle applies, then you can essentially just add them together. That's hopefully the simplest way I can kind of explain that. But for these distributed loads, the principle of superposition applies. Okay, so you're allowed to treat it like so. Any other questions for now? Okay, so next is non-linear varying loads. So this will not be in this course, but it might be in future courses, particularly if you do, mechanical, mechatronic, aerospace, that kind of stuff. That's the concept where we don't have a simple shape like a triangle or a trapezoid or whatever, and instead you've got to use integration and calculus to figure out like the equivalent load in this position. So yeah, if you were to think of this like an XY plane, again, except instead of the y-axis we've got W, right? WO is kind of your initial position, right? And then you can kind of have a function that describes the rest of that, whatever it might be. It might be a polynomial that describes it, etc. And then you can use the idea that integrating something is basically finding the area underneath that function or that curve, okay? And then in terms of a centroid, you basically do the integrated area multiplied by x and then divide by, okay, this probably makes less sense than just rewriting this r as this. It's basically the integral of W, that's on the bottom of the fraction. The top of the fraction is x times W, and then the integral of that. Okay, that was a pretty bad explanation. Hopefully you get what I'm saying. But my main point is that we won't be dealing with this today, or in this course. Okay, any other questions for now? Okay. Cool. So, methods for graphing internal forces. Okay, before I get into the actual methods, the first thing I want you to realize is that for solving beams, the first thing you want to do is always find the support reactions. It will help you greatly in trying to graph the internal forces, regardless of which method you do. So you've kind of learned the skills on how to do this, like last week. But yeah, it's basically finding the unknowns. So if this is a beam and you've got whatever loads on it, you're interested in finding these two reactions. Okay, that's the first step. Okay. Next, I think the best way to explain the two methods is in terms of something that you might already be pretty familiar with. So if you remember back to year 9 or year 10, I can't quite remember, and you're looking for, so the end goal, right, is you're looking to solve a quadratic, okay? Solve quadratic roots, let's say, okay? Now you've got methods to do it, right? You've got, I can just list 3. The quadratic formula, okay? And you've got factorizing, and there's complete the square, but let's not focus on that for now. Okay, let's just focus on factorizing versus quadratic formula. So quadratic formula, all that crap, takes a while, okay? So it's the slower method, but it will let you basically figure out the roots of any quadratic that you're looking for, including if it's got decimals involved or whatever, okay? So quadratic formula is very useful, but it's slow. Factorizing, which was like, for example, that or something, is basically finding the roots through finding the common factors. And this is a very quick way if you're familiar with like the basic principles of factorizing. So it's quick and it's easy and it's great for if you've got something simple, like if you've got whole numbers, for example. So this is the comparison that I'm going to make with the following methods that I'm going to show you. Okay, so you've got the graphical method and the algebraic method. Now the graphical method is essentially your equivalent of factorizing. So this is the factorizing equivalent. The output, by the way, I should probably mention, is that we want to graph the internal forces along the beam. Okay, so instead of finding the roots of a quadratic, we want to basically find a line that describes, or multiple lines that describes internal shear and internal moment, okay, for a beam. So that's your factorizing equivalent, and the algebraic method is your quadratic formula equivalent. And that kind of, I think, is the best way to describe the vibes of what these two methods do and stuff, right? So in terms of the graphical method, it is not able to solve every type of question. It's able to solve relatively simple questions, but it's very quick and it's easier. And algebraic method, you can solve any question with algebraic method, but it's slower and it's more tedious, okay? So hopefully that kind of gives you the pros and cons. So what I'm going to do is I'm going to teach you the graphical method first, and then I'm going to teach you the algebraic method, okay? And you might, as I'm teaching you the graphical method, you might have a lot of questions about where do these numbers come from? I don't really fully understand. But once you see the algebraic method, it will hopefully click, because the graphical method is a shortcut version of the algebraic method. So hopefully it will make sense when you see both. But it's faster and easier to understand graphical method, and then you'll see what the outputs are supposed to be, so that when you learn the algebraic method, it's not just random numbers like falling into place. Okay, any questions so far? So that's going to be our lesson plan. All right, so now I've got a question. Oh, sorry, yeah. Before I go through that question, I kind of want to go through a little brain teaser for you, okay? So this will kind of maybe help you in terms of solidifying your understanding of physics for your upcoming test. So if I've got a simple beam, like so, and I'm just going to copy it a few times. Okay, if we've got a simple beam, right, and I've put a point load in the middle, right, I want you to think about how much of the reaction goes into either support, right? You can probably imagine this is 50-50 if it's symmetrically loaded, right? Okay, if the point load is applied closer to one reaction than the other, where do you think most of the loads will go? Let's say, for example, this one ends up taking 75% of the load now, okay? And then this one takes 25, okay? One sec. What happens if we have a point load that's applied on the support itself? Okay, in fact, 100% goes into the support and 0, you don't even need to draw that because 0 goes into that support. All right, and this, as a matter of fact, is a simple way of describing how columns and beams transfer load into each other. So pretend this is like concrete column, and then this is a concrete floor that's suspended in the air. When you have a force, such as the loads which travel through this column from above, and then you've got a beam here, none of the loads from the columns and the loads above actually travel into the beam at all. 100% of it travels down and through the column underneath. Okay, so the column underneath acts as your support, and the column above actually acts as your point load when you're doing a free body diagram of the beam. Okay, so none of it interacts with the beam. It doesn't get more complicated when you've got offsets and stuff like that. But if this is perfectly aligned, yeah, that's kind of how that load transfer mechanism works. Yep.
If there was a force applied a little bit left to the beam going down,
Yep.
then would there be a moment on the beam?
This is a good question. Kind of, you're leaning into like second, third year territory for like civil engineering, but there's actually a lot that goes on. But if you model that like that instead, okay, it depends on whether you consider that column as pinned, as a pin support, or a rigid support, or there's something in between called a spring support. But if it's a rigid support, then it will absorb some of the moment. But if it's pinned, this is free to rotate. And so none of it becomes a moment in the column. But anyway, I'm getting ahead of myself because this is too much theory. But yeah, anyway. Okay, what happens if this beam is not simply supported, but in fact it's continuous and it's got this cantilever portion, and we actually have a force that's applied here? What happens to these supports? Yeah. I've actually got a beam here. Okay, one second. Fuck. It's gonna take a second, guys, sorry. All right, so we've got that situation which I was describing a second ago. If I apply the point load here, it kicks up, okay? So that's pretty important to understand how this works. Oops. This is kind of really sloppy. Okay, so it kicks up, right? So this thing kicked up like that, right? What does that imply? It implies that, in fact, this reaction on the left doesn't go up at all. It actually pulls down, right? So if that was properly attached and not just loose, right, that support would want to actually resist the beam from kicking up. And then this one actually becomes a larger force. So let's just say, for example, that would result in this support taking 125%, and this one's actually taking 25%, but just resisting going the other way. Okay, so this is good for you guys to understand it at a physical level, not just I'm applying these equations and then these are the reactions that I output. Okay, does that make sense? Okay. Before I go too far off course, let's go back to this. Now, this system will not behave the way that I said exactly, because we've got a restoring moment, essentially, like a point moment there. And so the way that the loads are distributed into the reactions will behave differently to what I just said. But I thought it was still good for you guys to know. All right, so this question says, for the loaded beam that you see, construct shear force and moment diagrams, and then state the value of the bending moment at point B being here. Okay. So I'm going to redraw this system as a free body diagram here. All right. And just a little recap from last week. I'm going to draw yellow highlights where we have unknowns. Okay. And to me, this implies that we can take the sum of the moments at A or at B in order to find the remaining unknown green line. Here in my working out, I've decided to take it at A, right? Which means we're going to be solving for BY first. Okay. So, one sec. I'm gonna find my notes so I don't have to do the calculations in my head. Okay. First thing is that when we're analyzing the system as a whole, and then we take the sum of the moments, right? You always add on counterclockwise moments, like point moments, as you can see here. Okay, so we're just gonna add on 1.6. The next thing is for BY, we've got, sorry, BY is, that's not BY. Okay, that makes more sense. So BY is causing a counterclockwise spin. So we add on BY, and the lever arm is 1 meter. And this point load going down is going to cause a clockwise spin, and therefore it's going to be negative when we're taking the sum of the moments. And its lever arm is 1.5. Okay. When you solve for this expression for the unknown BY, you will see that BY is equal to 1.4 kilonewtons. All right. So that gives us our first unknown. All right. Once we have that, we basically can look at the sum of the vertical forces, right? And then you would do AY plus BY minus 2 kilonewtons. So 2 kilonewtons being the point load pointing down. You ignore the point moment, right? When you're analyzing the force equilibrium. So because we worked out that BY was 1.4, the remainder is 0.6, right? So again, these numbers don't quite work out the way that I said before because we've got the restoring moment, the point moment. Okay, so that's that. If we're looking at the horizontal force equilibrium, the only force there is AX, and therefore there's nothing to react against, and so that horizontal reaction will be 0. Okay, so that's reactions. We've got those. That was just a bit of a recap, but that's not really new content. What is new content is graphing the internal shear and internal bending moment. Okay, the first thing I want to note before we do anything really is kind of standard notation or kind of like good habits for working out. It's that if you got your free body diagram, you kind of want to align the free body diagram, the shear force diagram, and the bending moment diagram in terms of its x-axis, right? So we know the beam is this long, okay? So however long I've drawn it, like so. The left should line up with the graph on the left, and the right should line up with the graph on the right when you're drawing the shear force and the internal moment, right? This is just a more clear way to like basically explain shear force and bending moment diagram. It's not a requirement, but I think it's a good habit. Okay. So again, I'm gonna just pull some random methods out of my ass, and this is the graphical method that I'm gonna show you. And it's not gonna make sense why I'm doing what I'm doing until I explain the algebraic method later, okay? So just bear with me. This is just gonna feel like completely arbitrary. So the first thing is that whenever you see so we're focusing on the shear force diagram at the moment, and so we're just going to think about the forces, okay? Whenever you see a point load including reactions like AY, there's going to be a discontinuity in your line, okay? So what do I mean by that? Our line is going to start at 0 kilonewtons, and then it's going to jump up in the same direction as the arrows for point forces. All right, so in our case, we've got a reaction of 0.6, so our line is going to jump up to 0.6, okay? You have to imagine that there is like a little man or something, and it's traveling along the beam, and we're going to go left to right. Okay, so this man's traveling left to right, and nothing is actually happening in this region, okay? Until this point here, right? But I guess, okay, I'm gonna draw the man continuing. There's kind of two ways to look at it, right? Because at a point moment, if you think about the force equilibrium versus the moment equilibrium, okay? At this point here, the point moment, nothing actually happens for the force equilibrium, but something does happen for the moment equilibrium, right? And so when we're thinking about the force equilibrium, we can actually ignore this point and just keep moving, all right? So the man's moving and he moves until point B. So essentially, this is a flat line up until that point there, in which By happens. And By is an upwards arrow with a magnitude of 1.4. Okay, so this line is going to want to jump up again by 1.4. Okay, so if that height that it jumps up is 1.4, and then that height down there was 0.6, the idea is the total height that we've gone up is 2 kilonewtons. Okay, it's in kilonewtons. Okay, so the man's still walking, and he keeps traveling along the beam, and nothing's happening up until the right-hand side, where we've got 2 kilonewtons pointing down. Okay, so that means the beam is going to be flat, and then we have 2 kilonewtons, which shoots back down to 0. Okay, and that will be our shear force diagram that we've just finished graphing. Okay, any questions so far? Okay, so here's the thing. What we're going to do is we're going to find the area underneath the shear force, which is going to help to inform our bending moment diagram. Okay, and we're going to split up our shear force diagram into like smaller shapes. All right, in as simple of a way as we can get away with. Okay, so the first thing is that we'll split this into shapes like so by height, but because we have a point moment here and we know that something happens with the moment equilibrium at that point, we're actually going to further subdivide this shape that we see on the left-hand side into 2 smaller rectangles, like so. Okay, and I'll explain the purpose of this as we do the moment diagram. But first we're going to find the areas of these shapes, okay? So the first thing to realize is that the geometry of the beam will stay the same in the x dimension on the shear force diagram as the same as the free body diagram, right? I'm going to start rubbing these dudes out. One sec. Okay. That's the first thing. The second thing is that we're interested in finding the areas of these shapes, right? And so we have to consider the height of these boxes as well, which is representing the kilonewtons of internal shear force, right? Okay, so that's what we're going to do. I'm going to find the areas, right? So we'll do base times height. So 0.5 is the base of the first rectangle, and then the height is 0.6. If you think about the units, which I'm just going to I'm going to write the units the first time around, but then to save space, I might not write the units again. The base is in meters, okay? And the height is in kilonewtons, right? So if you think about the physical, like, I guess, like, implications of this when we multiply the units together, we get kilonewton meters, right? Which is kind of a hint at where this is going, because this is the units that we use for our bending moment, right? Anyway. Okay, so we've calculated 1, we don't need to do 1 again. What we're going to do is we're going to calculate box 2, right? So box 2 is base of 0.5 meters and height of 2 kilonewtons this time, right? So that's going to give us 1 kilonewton meter. Okay, lovely. So that is our two areas, and I'm going to tell you how it works for when we graph the moment diagram now. So now we're going to do the bending moment diagram, and then we're going to graph it in kilonewton meters, okay? All right, so I guess the first thing to note is that, and I know this might seem really obvious to you guys right now, but the upwards direction that I'm going to graph is positive, okay? Just as it was here. The reason that's not obvious if you do civil engineering later is that actually it's going to be more conventional to have the positive direction going down for beams. I'll explain that later, or maybe another time. But yeah, anyway, so this goes the way that you think it does, and that's the convention, that's the sign convention that we go with in this course, okay? All right, so basically, if we look back at our system, we've got a beam which has a pin support on the left and a free end on the right-hand side over here, okay? So there's no support. For a bending moment diagram, the idea is that, like, if the very left or the very right of the beam doesn't finish with a rigid support, then you're going to expect your bending moment diagram to finish at 0 on both ends, okay? All right, so yeah, it's going to start and end at 0. Let's graph everything in between now. So if you think about a man walking on now the shear force diagram, okay? The idea is that everything he walks underneath will be captured in the bending moment diagram. So all the area that he walks underneath is going to be captured as a line that keeps going up, okay, on your bending moment graph. That is to say, this determines the rate of change of this line, okay? So if this is a rectangle, this will now become a rising line, okay? So after we've traveled one area of that one block, all right, at that stage, our bending moment is going to equal whatever we calculated for the first area. Okay, so that's 0.3 kilonewton meters, all right? Now, what's probably not going to be super intuitive until you see this done with the algebraic method is that now when we look at this point moment, right, which we have to consider now that we're looking at the bending moments, the internal bending moments, is that we know that this is a counterclockwise spin. So counterclockwise to us, right, intuitively implies that it's positive, right? But on a bending moment graph, a counterclockwise spin doesn't actually bring you up, right, as a discontinuity. It actually jumps you down, okay? This will make more sense when I show you the algebraic method, but just keep this in mind for now. So counterclockwise actually results in negative internal moment, right? Discontinuity that's negative. Okay. So we know that the amount that it jumped down, like the magnitude was 1.6, right? But it already started at 0.3. So really we're looking for this here. We're looking for like whatever number it goes down to. And that number is negative 1.3, okay? All right, so now we have that point there. And now we can add another block of 1, right? One area. That's going to be like here. So when we add that block of 1, right, which is 0.3. If we go on our calculator and we type negative 1.3 plus 0.3, we get negative 1, like so. Okay, now we have to deal with this larger block, right? And for this larger block, the magnitude is instead 1 kilonewton meter. Because the shear force diagram is indicating to us the rate of change, if we have a higher block, that means it's a larger rate of change, right? A larger positive rate of change. And so on our bending moment diagram, it's a sharper increase, okay? And what you'll find is when you type negative 1 on your calculator and you add 1, it's going to give you 0, right? So that should check out with what we'd expect as well. Okay, so that's basically our bending moment diagram and how we plot it. The question was asking at point B, which was the location of the right-hand side support, what is the internal moment? And the answer is negative 1 kilonewton meters. And you can see that on the graph. Okay. All right. Any questions about how that works? All right. I'm gonna give you guys a break. We'll do a break until 10:05 or maybe 10:06. So feel free to stretch your legs or grab some water or go to the bathroom or whatever, and come up the front if you have questions about anything. Oh, yep. Oh, yeah, the QR code? Yep. Oh, the YouTube channel, if you want it, is Sigma Lectures. So you can search that up on YouTube and you'll find me. Hello.
You know how ways uploaded for past papers?
Yes, sir.
Do you know if there's any way I can get more practice questions?
Have you done the civil workshop question? You've done this?
Yeah.
Have you done, so in my QR code, in that folder, there's a folder which says mining school or mech school, I can't remember which one it's called. There's a bunch of practice questions on there as well.
Okay.
I think.
I did the work.
Yeah.
I've done the workshop questions. 4 weeks, 1 week, 2.
Yep.
For the ENGG1300 ones.
Yep.
I haven't done those ones. And I had another question. What's the hardest? Okay, if you were to make an exam, what would be the hardest question you'd put in that exam?
So there's kind of two. So I didn't make this paper, by the way, so I don't know. I'm just guessing. But there's kind of two ways something can be hard, right? It can be time-consuming or complex in that way, or it can be conceptually hard, right? What you'll find, in my opinion, is that if you're able to handle any of the stuff in the workshops that I've covered, you're sorted for theory. Conceptually, that's as complicated as it gets. In terms of complexity, the difficulty is trying to juggle everything and making sure that you haven't made a silly mistake or something. And the civil workshop questions can get pretty complex. There'd be like 8 forces or something randomly on a beam, which is just tedious.
Yeah.
But yeah, that can be time consuming, and so you might find yourself running out of time, which is maybe something you want to practice.
Okay.
Yeah.
And one last question. So the roller support and the fixed support,
Mm-hmm.
I'm a bit confused as to what the meaning of those two are. It said that roller support, it could only have a certain amount of forces and stuff.
Yep.
But what does that really mean in terms of movements? Does it matter in terms of movements?
Trying to understand.
So for example,
the question a bit more.
if there's a question with fixed support on both sides and
Mhm.
there was a moment.
Okay. I see what you're saying. Okay. I'm going to draw a few things real quick and then I'll try to explain myself. So this is a beam that continues. So this is a line break. You've got reactions. So let me just draw this as a roller. And this is pinned. A roller support resists only your normal force, right? And then a pin support resists tangential forces as well. A fixed support or rigid support does those as well as a resisting moment.
So
Yeah.
that means that if I was to apply like a horizontal force on the roller support, there would still be a moment at the point. Like, yeah. So for example, if I
Yep.
apply like a like
Oh, like that.
yeah, so there would still be a moment on this point.
Okay, so if you were to apply a point moment at that support, what it's saying that the support does is it doesn't resist any of that,
Okay.
but it can redistribute the. Okay, so let's say you've got something like this. Let's copy this, right? Okay. Maybe I'll write it. Maybe yeah. Essentially, we know that this behavior will be something like this, right?
Yeah.
This point moment will redistribute this somehow. I can't remember which way is bigger.
Okay.
It will redistribute the way that the reactions. It will redistribute the way that the reactions. like the proportion of the load that the reactions take.
Okay.
Yeah, and it depends on the magnitude of that
Alright.
point moment. But the reactions themselves don't magically absorb moment, if that makes sense.
Okay.
Yeah, it will, yeah.
Would this come up in this exam or like is that?
No. I think you're overthinking it. Yeah.
Okay.
It's
alright.
like too complex. Yeah. No problem.
Thank you.
All good. Did you have a question? Yeah.
I have a question about the test
Yep.
and like kind of how points are allocated because
Mm-hmm.
I was looking at the practice test and they have like 30 marks
Yep.
for this one question that only has 2 parts. And
That's
I'm
funny.
like,
Okay.
why?
Okay, wait. Sorry.
maybe
Can
this
you?
is just like and it's the same like they're all just kind of the same like that in the what's it called like solutions. They kind of go back like they dissolve the forces and then they find the resultant force and then they like find the direction. So I'm just wondering, I don't know if you know, but like is there a certain way that they want us to be solving the questions or that will get us the 30 marks? Like, or like how?
If you answer the question, you'll get the full marks.
I know, like if we get the
Yeah.
right answers.
Right answer. Yeah, like I see what you're saying. Like you
So
mean
it's
like
like, I don't know
intermediate
how-
steps. You don't know how these
Yeah.
marks are broken up. The truth is, I don't know how the marks are broken up
Yeah, you
either.
can
It's
assume
kind of arbitrary, but
yeah.
if you can justify your working out with like reasonable logic line to line, that's enough to get you the mark, right?
Okay.
Because ultimately what you want is what the question's asking
Yeah.
you for. But yeah, obviously like if you, say you just, I don't know, say you set up this and like this is the problem that they give you or something and then you're just like, oh, okay, AY is equal to that, BY is equal to that, and that's your whole thing. It just gives you the answer, but it doesn't show your understanding of anything because you didn't write the force equilibrium line of working or whatever.
Yeah.
I would say that's not a very good that's not very good working out because the reader, the person marking, can't follow along with your working out. But as long as the reader is able to follow what's going on, that's good working out.
Okay.
Yeah.
Easy. And then I don't know if you know anything about like how many significant figures we're supposed to do.
Because
it never states in the question.
Yeah, it's kind of funny.
Or like do we just get to decide?
Significant figures.
Or
Fuck,
we
I'm
can
not
say
really
decimal
spelling this
places.
right. Significant figures versus, let's say, decimal places.
Yeah.
It's funny because in maths in high school, you probably used decimals, right? So to 2 decimals to 3 decimals.
Yeah.
In physics, they teach you that significant figures is the way to go.
Yeah.
It's funny because in engineering, I feel like we go back to decimals.
Oh, okay.
Because the degree of accuracy in engineering is more like shotgunny than in physics, to be honest. I would go to 2 or 3 decimal places.
Okay.
Yeah.
That's easy.
It's more of a vibe thing. It's not.
Cool, okay.
Yeah, like the reason they don't expect you to like have a certain amount
They
of.
don't really care.
Yeah, they don't care.
Okay, cool.
Yeah.
And then I had an actual question
Yeah.
about figuring out the angle with this tan y on x.
Okay. Is it alright if you ask this at the end?
Yeah.
What we'll do,
sorry.
no, it's all good. What we'll do is we'll continue the lesson, and then, we'll sort that out at the end because this goes back to a previous week. That's all.
Oh, easy.
Yeah, no
Thank
problem.
you.
All good. Okay. All right, guys, let's continue. Okay. Everything looks like it's not broken, which is good. All right. Let's do the second question. So, essentially, for the loaded beam shown, draw the shear force and moment diagrams. Determine the distance B measured from the left end to the point where the bending moment is 0 between the supports. So when I did the working out for this originally, I realized that I misread the question. So we'll come back to what this means in a second. But we're just interested in drawing the shear force and bending moment diagrams first. Okay, so that's what we'll do. As I mentioned before, the first step when you're looking for these things is always to find the supports, okay? So we'll just do that. So we're taking this on the moments at A, which means we're going to be solving for the unknown By. And we have to consider the, we have to consider all of the forces which induce a moment, right, around A. So there's By, the unknown reaction, which is spinning clockwise. So that will give us a lever arm of 2, and it will be positive. And then we have essentially this uniformly distributed load, right, which will act roughly there. And all we have to do is we have to get that uniformly distributed load's magnitude, right? Oh, wait, sorry. The first thing to note is that it's going clockwise, right? Since it's going clockwise, we're going to write a negative. Okay, next thing to note is that we want the magnitude of the equivalent point load pointing downwards there, right? Okay. So what we're going to do is get 1.5 kilonewtons per meter and multiply it over 3 meters. So 3 meters is how long the distributed load is acting over. All right, that's the first thing. The second thing is finding the lever arm of that arrow, and that is going to be half the length of the beam. So that will be, I'm just going to write, I'll write 1.5. Okay, so now we have this thing, which these two numbers, when multiplied together, basically found the magnitude of that force, and then this number here is your lever arm. Okay, cool. So that's that. When you rearrange this expression here for By, By, which is written down here, you get 3.375 kilonewtons, right? So that is the unknown By. All right, once we have By, we can do the force equilibrium, and we find Ay plus By, and then if we subtract 1.5 kilonewtons per meter, and that is over 3 meters, right? So again, that's the magnitude of the distributed load. We find that Ay ends up being 1.125 kilonewtons, right? Okay. The other thing is that the only horizontal force in this free body diagram is the horizontal reaction, and therefore it's not resisting anything, and then therefore the magnitude of it is 0. Okay, that's the support reactions. All right. The next thing, sorry, I'm going to correct this. The next thing is back to the shear force diagram, and we're going to use the graphical method again. In the next question, I'll show you the algebraic method, okay? But first thing we do is, starting at 0, we have a discontinuity that jumps up by Ay, and Ay was 1.125. So here we end up at 1.125, okay? Now, what's different between this beam and the one that we saw last question is this one doesn't have a uniformly distributed load acting over it, okay? And therefore, when we had our little man walking across, we had a little man walking across the free body diagram, it results in a flat line on the shear force, right? But now, if we have our little man walking across the uniformly distributed load, which is on the beam, in our shear force diagram, what is happening is this man's being dragged down by the uniformly distributed load, okay? And it results in this line, okay? So the reason I stopped the line there is because something else happens at B, right? But between A to B, you have a constantly falling line, which represents your shear force, your internal shear force, okay? So the question is, how do we figure out that point down there that's negative, right? And what you would do on your calculator is you would type 1.125, which is the starting point up here, but then we need to subtract by something, and that something is the magnitude of your UDL, which is 1.5, but that's in kilonewtons per meter, right? Whereas this one was in kilonewtons. We have to now multiply it by this distance that we've traveled, which is 2 meters, okay? So over 2 meters, right, we end up with negative 1.875 kilonewtons, okay? So now we're in the right units because the shear force diagram is in kilonewtons. So we have negative 1.875 kilonewtons, all right? I'll make that smaller. Okay. The next thing that happens is we have to consider the support reaction By. By was 3.375 kilonewtons, and again, this is a discontinuity. So we'll jump up to here, and on my calculator, what I would type is negative 1.875, which is the starting point, that's in kilonewtons, and then it's going to add on 3.375 kilonewtons. Which is going to give us 1.5 kilonewtons, okay? So that's the next line of working out that I would do. To here, okay? So that's 1.5. Okay, the next thing that happens is as the man is walking on this portion of the beam instead now, we've got the same uniformly distributed load, but it instead acts over 1 meter. Okay, so we've got the same slope. I kind of drew this not to the right scale. Give me one sec. Okay, maybe like that or something. The idea is I'm trying to redraw this line's slope. Okay. And then essentially it reaches 0. Okay, and the way that you can verify that is this was 1 meter. It's going over, this was 1 meter, and then this was a downwards push of 1.5 kilonewtons per meter. So if that's 1 meter, and it's going down 1.5 kilonewtons per meter, then you'll reach 0. Okay, so I guess let's rewrite it just for completeness sake. You would go like, that's positive. It's negative 1.5 times 1 is equal to 0. Okay. All right. That's positive, that's negative, that's positive. Okay, any questions so far? Okay, so when you're doing the graphical method, remember we're ultimately interested in finding the areas, right? And this time instead of rectangles, we have triangles, okay? So we know that the area of a triangle is half base times height or whatever, right? Okay, so if we look at this triangle, let's draw some numbers. We have triangle 1, we have triangle 2, triangle 3. If we look at triangle 3, no problems because we have the base, it is 1 meter, and we have the height, right? The height is 1.5, okay? So, like, we will be able to find area 3. But what you'll find is that we don't know the base for triangles 1 and 2. Okay, so how do we solve that problem? The information that we do know is that this distance here is 2 meters, right? So we can actually assign a length, right, which represents the base of that triangle, the first triangle, and we'll call it A. Okay. And this remaining length, right, if you think about it, if this was going over 2 meters and triangle 1 and 2's base, right, is 2 meters, but then you subtract off triangle 1, essentially the remaining length is 2 minus A. It's 2 minus A, right? So we actually have an expression now for the base of the second triangle as well. So we can actually, I'm supposed to say A. So we can actually find what A is through a method called similar triangles. And it's basically abusing the fact that we know the slope of this triangle is the same as the slope of this triangle, yeah? In other words, the rise of a run of the first triangle is equal to the rise of a run of the second triangle. Okay? So, what I mean by that, the rise for the first triangle is going to be this dimension here, okay? And this dimension was 1.125, okay? And the run, or the base of that triangle, is going to be A, okay? And we can equate this to the second triangle, okay? Where the rise is 1.875. Now, it actually makes... Okay, how do I say this? It's easier if you do this with just the magnitude of this height rather than the negative. Right? So imagine a triangle that's like that, and then this height of the triangle is actually 1.875. So if you think about it geometrically, we just care about the magnitude, okay? So anyway, we just type 1.875 here rather than the negative, okay? And then the run is 2 minus A. Okay, so that's the base of that triangle. So, if I give myself more room to do the working out, I'm running out. What we can do is we can cross multiply. Okay, so if we multiply that onto that side and that onto that side, we will get this. All right, and we can essentially group the like terms and then solve for A. Oh, wait, sorry. Yeah, it's that. Okay. We can group A and A from both sides, and we get A is 2.25 over 3, which gives us 0.75 meters. Okay, so now we've figured out this distance here, A. Okay, it's 0.75 meters. Okay, any questions about similar triangles? Yep. So I think it makes more sense if I have a bit more room, so let me just draw this. Okay. So, with similar triangles, right? How do I say this? Okay. We have a triangle that looks like this, and we're saying it is equal to a triangle that looks like this in terms of the slope, right? But if we want to make it a fair comparison, we actually need to equate the slopes as if they're triangles that look like this, if that makes sense. Okay? So ultimately, we only care about a triangle that looks like this. All right? And we only care about the magnitude because for a triangular shape, like the height is an absolute number. Like you don't get a negative height. Do you know what I mean? So really, we only care that about the fact that this is 1.875 here. Do you know what I mean? Yeah. And so if I was to draw it on here, it's like 1.875, it's like that. And then this is 1.125. And then the base, this is A. Okay. And then this is 2 minus A. So now we have a fair comparison because we can actually directly relate the slopes. Okay. Any other questions for now? Okay. So now that we know A, we can figure out the areas, right? So we're going to do half base times height. So for the first area, okay, so that's this triangle here, we'll go half, and the base is A. Oh, sorry, it's not A. It's 0.75, which was A. times the height, which is 1.125. And I'll type that into the calculator in a second. And then triangle 2 will go half. The base is this. So 2 minus A, 2 minus 0.75, which is 1.25 meters, right? That's 1.25. Actually, wait, no, I might just write that in the bracket so it's more clear what I'm doing. Like so. And then the height, which is this is pretty important. Make sure we include the magnitude now. Okay, so the area, we're concerned about whether it's positive or negative now. Okay. So that's, anyway, wait, I'll type in all the numbers at the end. For the third triangle, we're doing this, right? So half, the base is 1 meter, the height is 1.5 kilonewtons. Okay, now we'll compute all of these. The first one is 0.422 kilonewton meters. The second one, remember, because the triangle's dipping underneath the x-axis, it's negative, right? So it's a negative 1.172 kilonewton meters. And the third one is 0.75 kilonewton meters, okay? So now we have all these magnitudes. All right, let's graph it. So, if you think about the previous question, right? We had essentially no uniform distributed loads on the free body diagram, which resulted in a rectangle for our shear force, or constant shear force, and a linearly increasing bending moment diagram. Okay. Here we've got uniformly distributed loads, right, on our free body diagram, and therefore we have linearly decreasing shear force, and what you'll find is we actually are going to have a parabolic bending moment, internal bending moment, okay? So this will be a little bit harder to kind of wrap your head around, but we have a few bits of information which we have to like kind of piece together in order to get everything to work. Okay, so the first thing we know is the bending moment will start and end at 0, okay? So that's beneficial to us. The next thing we know is that after the man walks on these triangles, right, we're going to have 0.422 kilonewtons. So at this x location, we have 0.422 because that's after area 1 has been consumed, okay? The second thing is that at this location, if you type into your calculator 0.422 minus 1.172, you will get negative 0.75. What we will realize is that after both these triangles have been walked on, we are now at negative 0.75, okay? So this is when you add 1 and 2 together, okay? And ultimately, if you add 1 plus 2 plus 3 together, you should get 0, okay? So these are the points, and we have the magnitudes. Now we have to draw the correct bending moment shapes, okay, to connect everything together. We can kind of know that because these are triangles, these shapes have to be parabolic, okay? Now, one thing that's pretty useful, I think, to realize is that when you have 0 shear force, aka when the line intercepts the shear force is equal to 0, you're going to have a flat parabola. Sorry, the parabola is going to be flat at that point, okay? The slope of the parabola. In other words, you can expect it to be flat here, and you can expect it to be flat here, okay? I might do that in a different color. So it should be flat there and flat there, okay? That's the first hint that you have. And so, when you think about parabolas, right, there's only really 2 directions that it can go. It can go like that, or it can go like that, okay? Because we know it has to be flat, right, the parabola has to go like that, right, because it has to end up flat. And then what you realize is this is one continuous line expression. Like you'll realize this properly when we get to the algebraic method, which I'm pretty sure I'll have time to do today. This is a continuous line actually. And so you'd expect this to also be a continuous line, right? And then it's going to continue like with the same like line expression or function that describes that parabola, right? And so the parabola will continue. And in fact, here is where there's going to be a discontinuity, right? And then you've got another line expression that describes that other line. So how do you draw that? You know that's got to finish flat, right? And it's still going to be a parabola because it's triangular, right? So it can go like that or it can go like that. And because it's a finish flat, that's the final shape of that second bending moment line. Does that make sense? Kind of? It's kind of trippy. It requires a bunch of practice to kind of figure out the directions of these lines. But yeah, anyway, so that's how you would graph the bending moment diagram. Okay, I would like to do maybe at least one more question so that you guys can get a good understanding of the algebraic method. So if we don't have any more questions for now, let's continue. Okay, so as I mentioned before, like factorizing, like with finding quadratics, the graphical method can break down sometimes when you have something that's too complicated. You'll run into problems, right? And so when you see a triangularly distributed load, that's too much. That's it's very difficult to do with the graphical method alone. You'll struggle to graph the bending moment diagram. So therefore you have to use the algebraic method, which essentially that's where you have to cut the beam open and like derive functions for internal shear, V. You have to find V as a function of X, and you have to find M as a function of X, okay? And this involves cutting open the beam, and you'll see. Okay, so the first thing is that I've worked out the support reactions already. You've seen this enough times, so just assume for now we know what BY, AY, and BX are, okay? And we're interested for this question to find the maximum moment, okay? So what do we actually do? We have to cut open the beam, as I mentioned, and this point over here is point A, this point over here is point B. So I'm going to call this cut AB. And the reason I've done it like so is this implies the direction. And so if I write cut AB, it's kind of saying we're starting at point A and we're walking towards point B. Okay. The other thing when we're labeling this free body diagram is you have to describe the domain of X. Right, and so I'm saying that this represents everything between x is equal to 0 and x is equal to 3, non-inclusive. Okay, so that's the other thing. All right, now we get to the point where we're looking at the internal forces and we're going to solve for it. Okay, so the first thing you got to realize is that instead of a proper length, right, because this is the length, L is equal to 3 meters, we have a variable distance, okay? This variable distance, X, is basically going to describe everything from our starting point to where the cut is currently up to, okay? So this is a moving distance. So what I mean is that cut AB is over here when X is equal to a small number, and then when X approaches 3, it's going to be like over here or something. And we need a function of X that describes every point, okay? So, we can do two things, right? We can do the force equilibrium and the moment equilibrium about the cut in order to work out our internal shear function and our internal moment function, okay? So let's start with the internal shear function, right? Because this one's a little simpler to understand, okay? Sorry, before we do that, actually what I would like to do is basically tell you a little bit more about how a triangularly distributed load works, because let's say we're interested in finding the equivalent force, right, of this triangularly distributed load, but it's not so easy because we want half base times height, right? Okay, the base, when it's moving, right, the base is x, okay? So that's fine, all right? But the height also moves. The height also moves as you go along the beam. So we also need an algebraic expression to describe the height of this moving triangle that's growing in size, okay? The way that you do this, right, is first you got to realize that we can figure out the slope because it's a consistent slope, whether your triangle is this big or if it's the whole thing big, okay? So if we look at the whole thing big, its rise over run is it rose by 1.5 over 3 meters, okay? So actually the slope is 1.5 over 3 meters. Let's ignore the units for now. But we know that this is a consistent slope throughout the whole thing, right? Which means that this is 0.5. Again, I'm ignoring the units for now. So if I were to draw this triangle, all right, and we know the slope is equal to rise over run, okay, and we know the run, in fact, is x, okay, because that's the base of the triangle. We're interested in finding the rise, okay. So if we were to rearrange this equation, right, the rise is equal to slope multiplied by x, okay. So that's actually an expression that we can have for the height of the triangle, okay. So this is slope multiplied by x. Sorry, I'm trying to find space for all my scrollings. Okay. So, in other words, this height that's moving, okay, we can describe it with 0.5, which is our slope, multiplied by x. Okay. All right. Now we're ready to solve the force and moment equilibriums. Okay. So for the force equilibrium, we consider all the upwards and downwards arrows, right? So the upwards arrow, we've got 0.75, which is the upwards arrow pointing up. We subtract by v, okay? So v is our internal shear, and the internal shear is going to vary along the beam. Okay, so this is the function that we're actually solving for. So if you think about this is like v is a function of x. Okay. Okay, so that's going down. The other thing that's going down is our triangularly distributed load, which we need to resolve into kilonewtons. Okay, so half, we do base. Okay, the base is x times height, right? And the height is 0.5x. Okay, so this is the magnitude of that triangle that's pointing down, okay? And this is ultimately the function that we care about. So if we rearrange this thing for the function, okay, we go, v is a function of x, is equal to 0.75 minus, and if we simplify this, we get 1 over 4 x squared, okay? So this is basically our expression, which is going to help us graph the shear force diagram. Okay, the next thing is moment, all right? So if you think about this free body diagram again, and what we're going to do is we're going to take the sum of the moments about the cut, okay? So the first thing is that you've got a counterclockwise moment, right? So it's going to be positive, right? And then this is a function of x. So that's what this is. Okay. So that's that thing resolved. The next thing is we've got the force of 0.75, and it's counterclockwise, right? Sorry, it's clockwise. It's clockwise. Wait. Clockwise. Yes. It's clockwise, and therefore it's going to be negative. Okay. Sorry, there's too many bloody directions. So this is negative 0.75, and then the distance or the lever arm away it is x. Okay. Now next we have to resolve our triangle, right? So for our triangle, it's going to be positive because this triangle is going to cause a clockwise spin about the cut. All right, so it'll be positive, and then let me give myself a bit more room. So it's going to be positive, and then we're going to do the magnitude, which we actually worked out a second ago already. So I'm just going to copy this over. So that's the magnitude, yeah? And then we're going to also multiply by the lever arm, okay? And the lever arm, aka the distance from this point to this point, is going to be x on 3. Okay, so x on 3 is our lever arm. So what we're going to do is we're going to rearrange for m as a function of x, and we find that it's equal to this. So you can see a few things, right? Let me just put this in blue highlight. So that's our function of our internal moment. The first thing you might notice is that in terms of polynomial orders, this triangularly distributed load is going to result in a quadratic function for our internal shear, and it's going to result in a cubic function for our bending moment. So that's why it's very difficult to do with just the graphical method alone. All right. That's the first thing. The second thing you might notice is when we considered the directions which corresponded to our left-hand notation, when we do the force equilibrium going up, you've got a negative. I might do this in like red or something. You've got negative v. But when you do the same thing for the moment, right, you've got positive m. Okay, so this and this have like opposing, I guess, signage, right? Which is kind of why, going back to what I was saying about the point moment thing, it's why the shear force, right, when you graph it, goes in the same direction as your external forces, right? The internal shear goes in the same direction as your external forces, but your external moment will go in the opposite direction of your point moments. Okay, so fundamentally the signage is just different. Okay. Sorry, going back to this question. Okay. Just, I know I did a bunch of rambling. I want you to focus on two things. The first one is the shear force expression, and the second one is the moment expression. So for the shear force expression, it starts at 0.75, which is up here, okay? And we're just graphing a parabola, and so it just goes down like that. There's two ways you can work out where it ends up on the right-hand side. The first thing you can do is instead of x, you can plug in L, which is 3 meters. So if you plugged in 3 meters, you would find this expression, v as a function of x is equal to negative 1.5, okay, when you plug that in. That's one way you can do it. The other way you can do it is using your understanding of the graphical method, because the graphical method will speed things up significantly. You know that the reaction on the right-hand side is 1.5, okay? And so it implies that there's a discontinuity, aka a jump, of 1.5, which brings you back to a shear force of 0 on the right-hand side. I don't know if any of this is making sense, or I'm just like saying random shit. Does this kind of make sense? Yep.
So do we always need to find the second expression? Because isn't that just the integral of the first expression?
That's true. Not always, because if you have a point moment, like so, it's not the integral anymore, because the point moments will interfere with the way the shear force will behave. Yeah, but yeah, no, that's a good point. That's one trick that you could do if you really wanted, but if you think about it, I think this is a more clean workflow, just to do the moment equilibrium rather than, yeah. I haven't really tried that way, but you can experiment and see how you go if you like. Okay, any other questions for now? Okay, for the moment, right? Oh, sorry, what I'm trying to say as well is, you know when you integrate, there's like plus c. Yeah, that c will also not always be 0.
But can we do a definite integral between so for this one, we do a definite integral between 0.75 and the other
I kind of see what you're saying. It might work. Yeah, I just haven't tried that way before. You can play around with it if you want, and if it works mathematically, then that's a good method. Yeah. Okay. All right. So bending moment. All right. That's represented by this line. Okay. So it's a cubic, and it looks something like this, like a little bit of an offset parabola, right? We're interested in the maximum bending moment, okay? And there's a few ways to do this, but I think the simplest way is actually to look at the shear force diagram and figure out where, let's call this distance C, it's to figure out where the shear force equals 0, okay? So I'm just going to move this. So if you set this to 0, that's where this line is, okay? And you're looking for x, okay? So if you rearrange and you find x, it's going to be plus or minus some number. It'll be plus or minus 1.732, aka it goes out here on the left somewhere as well, but we don't really care about the negative point. We just care about the positive point. So x is equal to that, okay? And in fact, that is what c is going to be, right? So c is equal to 1.732 meters. Okay, so c is that distance, all right? That distance is going to correspond with the peak of our bending moment diagram, because that's all of the positive. That's all of the positive shear that you've walked over, I guess, right, to reach that point there, okay? So to find our max bending moment, what we do is we find the internal moment when we plug in x is equal to c, okay? So that's 0.75, and instead of x, we plug in c, and 1/12, and instead of x, we plug in c, and cube it. And of course we know c is equal to this thing. All right. So essentially, m max will be 0.866 kilonewton meters. Okay. Like so. All right. Any questions? Okay. I realize I missed something from the previous question. It's my bad. From the previous question, right, it said determine the distance b measured from the left end to the point where the bending moment is 0 between the supports, okay? So what I actually found before was this distance, which is where the shear force is 0, but that's not necessarily where the moment is 0, okay? So let me just rub out a bunch of crap. So if you think about it, right, where the moment is 0, if you think about this graphically, is where you've added one triangle of shape 1, and then you've added that triangle again, but going negative, right? And it's where you reach the arc of your parabola, and you go the same distance, and then meet, like, at the x-axis, right? And so in other words, if we travel A and then A again, we get the distance we're looking for. So this is 0.75. That's equal to 0.75. B is 1.5 meters. That's what I'm trying to say. Okay. So B is just the distance from the left end of the beam to the point where the moment is 0. Okay. Any other questions for now? So obviously we're not going to have time to do the 4th question in full because it's nearly 11. But what I will do is I'll explain how you would do it, and it's good practice. Okay. So the way you would do it is... Okay, here's a question. A shaft is supported by a smooth thrust bearing at A and a smooth journal bearing at B. Draw the shear force and moment diagrams for the shaft. So that's this thing here. Which looks different to what we've seen before, because before we were looking at beams, and this is more like a mechanical engineering thing. You have bearings instead of roller and pin supports and stuff. But fundamentally it behaves the same, and I guess one other thing to note is that they're dealing with different units, so newtons and meters rather than kilonewtons and meters. The reason is in mechanical engineering, like the scale is usually more in the order of newtons, whereas for beams, which is like in large buildings, right, which are like very heavy and stuff, you usually work in the order of kilonewtons. Okay, so the first thing you realize is that a thrust bearing and a journal bearing are pretty much just pin supports and roller supports, effectively. Because if you think about it, a thrust bearing is just something that will resist it will support not only the normal forces, but also resist tangential forces. Whereas a journal bearing, which is something that allows this rod to freely slide through it, is basically a roller. It's a roller support. Okay. So that's the equivalent, right? These are now mechanical engineering terms. Now, in terms of how you approach this question, right? Because it's kind of annoying. The first thing you'll realize is that there's quite a lot of different forces, right? There's this uniformly distributed load, there's this triangularly distributed load, there's this point load, there's this point moment, okay? So this is why it's good practice, because we've got added complexity. And so you can kind of slowly do this in your own time. But if you try to approach this from the left-hand side, okay, you'll run into a problem, right? If you try to do this, right? When you reach the point between B to C, what you'll find is if your dude is traveling to the right, it's now a trapezoidally distributed load rather than a triangularly distributed load. And as I mentioned before, for a trapezoid, it's really annoying because you have to split it into a triangle and a rectangle, right? And so you can do that. It's very tedious and painful. Or you can be clever and you can go right moving left. So if you go right moving left, all of a sudden, you're just looking at a beam that has a triangularly distributed load being applied onto it instead of a trapezoid. And so you don't have to do the principle of superposition and all that. So that's what I do in this solution. First thing was support reactions, as always. And then here I've done the cut from C to B. So remember, this is important. If you're going right to left, I would say it's good practice to notate it from starting point to the end point. So if C is over here, B is over here. And then X is actually traveling the other way now. We know the slope, and therefore we know the height of this growing triangle in size. And then you can find expressions for, similar to how we did it before, you can find expressions for V and M. Okay, and then when we're graphing it, okay, what I've done is that purple line that you can see is the internal shear force and function that I derived, but what's interesting is I've made my life easy by using the graphical method, all right, on the left-hand side. So the graphical method will bring me like up until this point, and it's a lot faster than finding more algebraic expressions. And on the right-hand side, I've done the other method. So you can kind of mix and match these methods if you like, as long as you can ultimately find what how your beam's internal shear and moment vary along it. Okay, that's the most important thing. So yeah, anyway, you can see that there's an integral when you're trying to find the area if you really wanted to. And then yeah, so this purple line represents this moment expression, like so. Okay, any questions about this and the approach? Okay, this one's a good one to do as practice. But anyway, this doesn't really immediately concern you guys because you're probably more concerned about your test that's coming up on Saturday. Okay, thank you for joining the class. I'll see you next week. And good luck.